Hello, this lesson will be about area, how it's defined, and where our area formulas for most common shapes come from. This lesson is intended for middle school and high school students who are either first learning about the concept of area or students who are reviewing to improve their overall understanding of area. Area is defined as the amount of two-dimensional space that a shape takes up. Area can be thought of as the number of 1 unit by 1 unit squares that can fit in a particular shape without having any excess squares or excess space in the shape. For example, here is a polygon, or a figure with 3 or more sides. If we define this to be our 1 by 1 unit square, then the area of our polygon is the number of these 1 by 1 unit squares, or we could just call them unit squares, that take up the same space as our polygon. It is important to note that if we partition or divide a shape into multiple other shapes that together create the original shape, then the total of the areas of the smaller shapes will equal the area of the original shape. For instance, in this example, we have the total shape P. This is P for polygon. We have divided it into 3 smaller polygons, P1, P2, and P3. The area of P is equal to the area of P1 plus the area of P2 plus the area of P3. Now we will show you how we derive the formulas that we commonly use for many shapes to calculate the areas of many shapes. First, we will demonstrate the area of a rectangle. A rectangle is a quadrilateral or a 4-sided polygon with 4 right angles. Rectangles have opposite sides congruent to one another. Take one of the sides and call it the base, B. Let the other side be the height, and let its length be h. In this case, b and h are variables representing the length of the base and the length of the height. We can divide the rectangle into h smaller rectangles, each of height 1 and base of length b. In each of these smaller rectangles, we can fit unit squares along the rectangle. There will be able to fit b total unit squares side by side. And we have h of these smaller rectangles. So when we stack up these smaller rectangles to make up the total original rectangle, we have h smaller rectangles, each with b unit squares. That gives us h times b, or b times h, total unit squares in the area of the original rectangle. This means that the area of our original rectangle is b times h. Now let's look at a square. A square is simply a rectangle with all sides being of equal length. So a square still has the same characteristics that a rectangle has, and still follows the base times height area formula. However, in this case, the base and the height have the same length. This means that the area can just be simplified to s squared, where s is the length of any side. Because all the sides are equal, s equals b equals h. So the area is simply s times s, or s squared. A bit more complicated than the rectangle and the square, our next shape is the triangle. Triangles are 3-sided polygons. Recall that there are 3 types of triangles: right triangles, acute triangles, and obtuse triangles. We will first look at acute triangles. The height of a triangle is defined as the length of the segment from the vertex opposite the base to the line containing the base, perpendicular to that line. So if you let one of these sides of the triangle be the base, then you would take the vertex opposite that base, and you would draw a line from that vertex to the base that is perpendicular to the base. The length of that line segment will be the height of the triangle. The length of the base will be the base of the triangle. First, we will look at acute triangles. Acute triangles are triangles with no angles of measure greater than or equal to 90 degrees. Let one side be the base. Now we construct the segment that gives us the height h. Now construct a rectangle around the triangle, as shown in this picture. Observe that this rectangle consists of our original triangle and 2 smaller triangles. However, the height segment splits up our original triangle into 2 smaller triangles as well. Notice that we can label these triangles T1 and T2. T1 is the same shape, is congruent to the smaller triangle within the rectangle. T2 is congruent to the other triangle within the rectangle. This is easy to show because the height h divides up the rectangle into two smaller rectangles, and rectangles have opposite sides congruent or of equal length. And like I said earlier, the area of any shape, any polygon, is the sum of the areas of the polygons that make up the shape. So the area of the rectangle can be seen as the area of T1 plus T1 plus T2 plus T2. However, the area of our triangle is the area of T1 plus the area of T2. So the area of our triangle is the area of T1 plus the area of T2. The area of our rectangle is 2 times the area of T1 because we have 2 T1s, and plus 2 times the area of T2 because we have 2 T2s. You can factor out the 2, and we will get that the area of the rectangle is 2 times the area of T1 plus the area of T2. This is the same as 2 times the area of our original triangle T. Dividing by 2, we now have that the area of our original triangle is 1/2 the area of our rectangle. If you recall from our previous formula, the area of the rectangle is simply the base times the height. So this means that the area of the triangle is 1/2 times the base times the height. This works regardless of which side we use as the base. Now let's consider a different type of triangle, the right triangle. Recall that a right triangle is a triangle with exactly one right angle, or one angle with exactly 90 degrees. If we let the base be the side opposite the right angle, known as the hypotenuse, then we can just use the argument that we used for the acute triangle. If we let one of the two other sides, called the legs of the triangle, be the base, then you simply construct a rectangle, as shown in this diagram. The area of the rectangle is the area of our original triangle plus this other triangle that we have. This other triangle is congruent to our original triangle because it also has base b and height h. The height h is simply the other leg that is not the base, because this is perpendicular to the base, because it's a right triangle. So the area of the rectangle is 2 times the area of our original triangle. This means the area of our original triangle is 1/2 the area of the rectangle. The area of the rectangle is simply base times height. This implies that the area of the original triangle is just 1/2 base times height. This is interesting because it's the same as our formula for the area of the acute triangle. Now look at an obtuse triangle. Obtuse triangles are triangles with one angle of measure greater than 90 degrees. If we let the base be the side opposite the obtuse angle of the triangle, then the area formula holds from the same argument in the acute triangle case. If we consider one of the other two sides of the obtuse triangle as the base, then we can construct this perpendicular line for the height h. Recall that h is the length of the segment that goes from the vertex to the base perpendicular to the base. However, it's not possible for the segment to connect to the base because this is an obtuse angle. But we can make a height segment that is perpendicular to the line containing the base. This gives us one large triangle and another smaller triangle. Let our original triangle be T, and we're going to call our new small triangle T1. The area of the total triangle T and T1 together is 1/2 base times height, where the base is b plus x. And the area of our small triangle is 1/2 base times height, where the base is x. The area of our triangle T plus the area of our triangle T1 is the area of the sum of the two triangles. So if we subtract, we can find that the area of our original triangle is just the area of the big triangle minus the area of our new small triangle. Like I just said previously, the area of the big triangle is 1/2 times b plus x times h. the area of the small triangle is 1/2 times x times h. We can distribute the 1/2 and the h in the first part of the expression and get that the area of our original triangle is 1/2 bh plus 1/2 xh minus 1/2 xh. The two 1/2 xh's cancel, and so we get that the area of our original triangle is just 1/2 times the base times the height. This is a very interesting fact because it shows that no matter what triangle we have, and no matter what orientation it is in, the area formula remains the same, 1/2 times the base times the height. This is exactly half of the area of the rectangle with the same height and base. Now we are going to look at another four-sided shape, another quadrilateral. We are going to look at the trapezoid. A trapezoid is a quadrilateral with exactly one pair of parallel sides. To compute the area of the quadrilateral, we're going to let one side of the two parallel lines, the two parallel sides, we're going to call one B1 and one of them B2. Let's just say that B1 is the longer of the two. Now we're going to construct a diagonal. A diagonal is simply a segment going from one vertex to an opposite vertex. You will notice that the diagonal will split up our trapezoid into two smaller triangles. We're going to call these T1 and T2. It is easy to see that the distance from B1 to B2 is the same for any point on B1 and B2. So the height is the same for T2 and T1 because they have the same two bases. And so the height is the same. And so the area of a triangle is 1/2 base times height. The base of T1 is B1 and the base of T2 is B2. So the area of the trapezoid is equal to the area of T1 plus the area of T2. This equals 1/2 B1h plus 1/2 B2h. We can factor these together to get 1/2 times B1 plus B2 times h. This will be the area of our trapezoid. This is interesting because it shows that the area of a trapezoid is very closely related to that of a rectangle. The only difference is you take the average of the lengths of the bases. Our next shape, and arguably one of the easier shapes to find the area of, is the parallelogram. A parallelogram is a quadrilateral with two pairs of parallel sides. We're going to let the base be one of the sides, B. The height, again, is the length from a vertex opposite the base to the base. So if we let one of the segment from a vertex opposite the base to the base be the height h, we will observe that this actually sections off a triangle from the rest of the parallelogram. A parallelogram actually has opposite sides being of equal length. So we can actually rearrange and move this triangle to the other side of the parallelogram, where these dashed lines are. So if we move this triangle on the left of the parallelogram in our picture to where the dashed lines are, we just get a rectangle with base B and height h. And because all we're doing is rearranging the parallelogram and not changing its shape, this implies that the area of the parallelogram is the same as the area of the rectangle. The area of the rectangle is simply base times height, or B times h. So this means that the parallelogram's area is just B times h. This is actually interesting because if you think about it, a rectangle is also a parallelogram, and so is a square. And our areas for those is the same as the area for any parallelogram. Next, we're going to look at a kite. A kite is actually one of the more interesting shapes, in my opinion. A kite is a four-sided shape, or quadrilateral, in which it has two pairs of adjacent sides that are congruent. This means it has two pairs of sides that are next to each other that are of equal length. Look at this picture. We have a kite. The top two sides are both of equal length, and the bottom two sides are both of equal length. We are going to construct the two diagonals. These two diagonals will divide up our kite into 4 triangles. Now we're going to construct a rectangle around the kite, as shown in this picture. This rectangle consists of 8 triangles, the 4 triangles of our kite, and 4 new triangles. These new triangles are actually congruent to the triangles in our kite because they have equal sides, or sides of equal length to the triangles in our kite. This means that if we let the triangles in our kite be named T1, T2, T3, and T4, then the area of the kite is simply the area of T1 plus the area of T2 plus the area of T3 plus the area of T4. The area of the rectangle is 2 times the area of T1 plus 2 times the area of T2 plus 2 times the area of T3 plus 2 times the area of T4. We can factor out the 2, and this shows us that the area of the rectangle is simply 2 times the area of the kite. The rectangle has base and height that are of lengths of our diagonals. We call these D1 and D2. So the area of the rectangle is simply base times height, which are the 2 diagonals. So this equals D1 times D2. The area of the kite is 1/2 the area of the rectangle. So it's 1/2 the base times the height, which means it is 1/2 times D1 times D2. So far, we have shown that the area of the kite is 1/2 D1, D2, where D1 and D2 are the lengths of the 2 diagonals of the kite. Our last polygon that we're going to look at is the rhombus. The rhombus is simply a quadrilateral or 4-sided polygon where each side is congruent. This means that each side is equal length. In fact, because each side is of equal length, this implies that the opposite sides end up being parallel. Because the opposite sides are parallel, we can calculate the area of the rhombus the same way that we calculated the area of the parallelogram, using the base times the height. But because each side is congruent length or equal length, a rhombus is actually a type of kite as well. So we can calculate it with the diagonals like we did with a kite. This means that we have 2 equivalent area formulas for a rhombus. The base times the height. In this case, our base is S, so it's S times H, where H is the height. Or it is 1/2 times the diagonals, 1/2 D1, D2, where D1 and D2 are the lengths of the diagonals. So far we have shown how to calculate the areas of many different polygons. We looked at squares, rectangles, triangles, including each of the 3 kinds of triangles. We looked at parallelograms, trapezoids, kites, and rhombuses. We're going to end this lesson with circles. Circles are arguably the most difficult to intuitively think about. A circle isn't a polygon because a polygon has at least 3 sides. A circle can be defined as simply the collection of points that are equal distance from some point called the center. So if you take some center, then you take every point that is the same distance away from the center, and that is your circle. This means that a circle is a perfectly round shape. You may recall that a circle has a diameter, where the diameter is a segment connecting 2 points on the circle that goes through the center. Recall that a radius is the distance from 1 point on the circle to the center. The radius is 1/2 the diameter. Also recall that the circumference is the length around the circle. It can be thought of as the perimeter of the circle. You may know from earlier classes that there is a number called pi. Pi is about 3.14, and pi is the ratio of the circumference to the diameter. This means that pi times the diameter equals the circumference. This is going to be important in our derivation of the area formula. Now we are going to construct multiple diameters, multiple segments from 2 points on the circle that go through the center. This will section off the circle. We are going to section off the circle into congruent pieces. First, we're going to section off into 4 congruent quarters, like shown in this picture. We can then take these quarters and pair them up like we did to the right. This gives us an interesting round-looking shape. You might notice what we're getting at so far, but it doesn't matter because we will get to it soon enough. This shape is somewhat reminiscent of some of the earlier shapes we looked at. Let's see how it changes when we divide up the circle into even more pieces. In this case, let's divide up the circle into 8 congruent pieces. When we divide it up into 8 pieces, we get this shape. We then put these pieces together, like shown. You may think that this looks kind of like a parallelogram already. Well, interestingly enough, when you divide it up into more and more pieces, like we shown in this last picture, the shape that we get by putting the pieces together actually becomes closer and closer to a rectangle. When you end up dividing it into as many pieces as possible, approaching infinitely many pieces, the shape that we get by putting these pieces together becomes closer and closer and closer to a rectangle. Eventually, if we theoretically cut it up into infinitely small pieces, infinitely many pieces, we will eventually get a rectangle. Because how we designed the rectangle, the rectangle's height is simply the radius, because each piece has length equal to the radius. The rectangle's base is half of the circumference of the circle, because the base consists of the widths of half of the pieces. The circumference of a circle is pi times the diameter. So 1/2 of the circumference of the circle is pi times the radius. This means that our rectangle has height r and base pi times r. The area of the rectangle is equal to the area of the circle, because we are simply rearranging the pieces in the circle. The area of the rectangle is simply the base times the height. So it is pi times r, or pi times r squared. This is the area of a circle. Using these different area formulas, we can even find formulas for more complicated shapes by sectioning them off into smaller known shapes. These are very important results, as they are the building blocks of finding the areas of more convoluted shapes in real-world applications. It is important for finding the volume of shapes in 3 dimensions as well. By reasoning through each shape individually, we have come across fairly intuitive reasons for where our area formulas for polygons and circles come from. This is an important big question from our unit in geometry, an important concept for many people to understand. Thank you for watching, and if you have any questions, feel free to ask or comment. Thank you. Take care.